Hi. Well, in the previous video, we finished description of vectors and operations of vectors. And I promised you that now we're going to move to operation laws on matrices. But before we go to operation laws on matrices, maybe let's review operation laws in regular algebra. So the ones that you learned in elementary school. Okay, so here is the 5 operation laws that we actually want to discuss over here. So first, we've got commutative law of addition, which basically says that in case of numbers, a plus b is the same as b plus a. And then we've got commutative law of multiplication, which says that a times b is equal to b times a. Then we've got associative law of addition, which basically says that it doesn't really matter in which order we are adding different elements. So we've got different numbers. So a plus b in parentheses plus c is the same as a plus b plus c in parentheses. And the same associative law we have for multiplication. Basically, again, as law just says, that it's irrelevant in which order we multiply numbers. And finally, we've got distributive law, which says that a times b plus c is the same as a times b plus a times c. Okay, now, some of these laws work as well in case of matrix algebra, but not all of them. Okay, so let's start with matrix addition. And let's now move to commutative law. Now, if we want to add matrix A to matrix B, the question is whether we're going to get the same if we add B plus A. Of course, please remember, conformability conditions must be fulfilled at the beginning, so they need to have the same dimensions. So they both need to be n by n. So, does this law work? Well, it does. But, instead of demonstrating it, let's just prove it. Okay, so look, a plus b is, well, matrix A is a collection of elements Aij. So we add these elements Aij to the collection of elements Bij in matrix B. And look, how do we perform addition? Well, we simply add all appropriate elements. But because we've got commutative law of addition, it's not a problem to change the order. Maybe next step. But of course, this is the same as Bij plus Aij, and this is equal to B plus A. So we clearly see that addition is commutative, right? So it really doesn't matter whether we multiply, whether we add A to B or we add B to A. Okay, so now let's go to associative law. Okay, so now we will ask if A plus B plus C is the same as A plus B plus C. Again, we are assuming that all conformability conditions are met, so we can add all 3 matrices. And now, again, as it happens to be, associative law works. Again, we can quite easily. Okay, so look, if we have A plus B plus C, we already said that this is simply Aij plus Bij. And we add to it a collection of elements Cij. Now if I add those, I will get Aij plus Bij plus Cij. And now, if I'm gonna rewrite it, look, it really, because we have an associative law of addition for numbers, so for scalars that we've got here, it's not a problem that we rearrange this a little bit, right? So we can get the same from Aij, Bij plus Cij. And this is nothing more than A plus B plus C. So we found out that associative law works very well in case of matrix addition. Okay, now let's go to matrix multiplication. And again, we're going to start with commutative. Okay, so now we are asking whether A times B is the same as B times A. Well, right away we can figure out that this cannot be always true. Why? Well, let's see a very simple example. Let's just say that this matrix is n by n, and this matrix is n by k. So, if I can multiply those matrices, but over here we've got n by k times n by n. So, we cannot even multiply those matrices. So we see that it is quite impossible to do so. Okay, but what if the matrices actually have the same dimensions? Maybe then this will work. Let me illustrate this with an example. Okay, so I've got matrix A given by 1, 2, 3, 4, and matrix B given by 0, 6, negative 1, 7. Okay, so let's calculate A times B. So we've got 1, 2, 3, 4, 0, negative 1, there was 6, and 7. Okay, this will give us another chance to remember how do we multiply matrices. Of course, we can multiply those because those are two square matrices. So we go 1 times 0 plus 2 times 6 is 12. Then over here, 1 times negative 1, it's negative 1, plus 2 times 7, 14, so we've got 13 over here. Then we go 3 times 0, 0 plus 4 times 6, 24, and here we have 3 times negative 1, negative 3, 4 times 8 is 28, so we've got 25. Okay, now let's see what happens when I multiply matrix B by matrix A. So now I'm going to start 0, negative 1, 6, 7, 1, 2, 3, 4. Okay, so again, 0 now, 0 times 1 is 0, negative 1 times 3 is negative 3. 0 times 2, negative plus negative 1 times 4 is negative and we've got 6 times 1 plus 7 times 3, 21 plus 6 is 27. Then we've got 12 plus 28, so we've got 40. Okay, and we can clearly see that this does not hold for these two matrices, right? So, now, should we prove that this doesn't work? We don't need to. Why? We already showed that there exists at least one example when this commutative law does not work, and if it does not work with this one example, it will definitely not work. We cannot treat it as a general rule. Okay, but this actually gives us the opportunity to dig a little bit deeper, into matrix multiplication. Because look, now we should see that it actually really matters from which side we multiply two matrices. So look, if I have matrix A times matrix B, here you can say that what are we doing? Here we pre-multiply by A. So matrix B over here was pre-multiplied by A. And over here we will have a situation the matrix A was post multiplied by B. Okay, so we should keep in mind that whether we multiply from which, whether it is important from which side we will be multiplying the matrix. Because of course A times B is not the same as B times A. But there's one upside to this, because as it turns out, commutative law works in case of multiplication by scalar. Okay, now, so what does it mean? That some constant k, so some scalar k times A is the same as A times k. Now, can we prove it? Quite easily. No. If we start with k times A, right? This is the same as k times collection of elements Aij. How do we perform this operation? We multiply each element. But we know that multiplication of numbers, so of elements of a matrix, is commutative, right? So we can write it as Sijk. But this is the same as Aij times k, and this is the same as A times k. So as it turns out, it really does not matter from which side we are going to multiply the matrix. Okay, so now that we have done multiplication by scalar, we can move to associative law of multiplication. Associative law of multiplication. Okay. So now let's consider the case that we've got three matrices. Matrix A, matrix B, and matrix C. And we're going to get out of this a matrix A, B, C. Now, as it turns out, the matrix multiplication is associative, right? It works. So it doesn't really matter if I multiply the first two matrices or if I multiply the latter two matrices first. We will always get the same result. But there is a different problem that we will encounter over here. Of course, look, in case of matrix multiplication, we must have conformability conditions met. So look, let's just say that this matrix is a matrix M by K, right? So if I want to be able to multiply this matrix, matrix A, by matrix B, then matrix B must be with the dimension of a dimension K by, let's just say, some L. Now, if I in turn want to multiply matrix B by matrix C, then matrix C must be of a dimension L by N. So look, those, when you look at those matrices, we can say that those two are adjacent matrices. And of course, those two are also adjacent matrices, right? Now, so for associative law to take into place, first, conformability conditions must be met, which requires from us that all adjacent matrices have the condition met that the number of columns in the first matrix is the same as the number of rows in the second matrix, and the same, of course, over here. And now look, even though we have a lot of dimensions, we can right away guess what will be the dimension of this matrix, because the only thing that matters is the first and the last one. So this matrix over here will be of dimension M by N. Okay, and look, because we are not making a proof here, because that would be rather troublesome, let's do a nice example that will illustrate that everything that we said does for. Okay, so in our example, we have matrix X, vector X, x1, x2. I've got matrix A, A11, 0, 0, A2, 2. And now look, what I want to find is expression X, A, X prime. Okay, as you will, oh my god, I'm sorry. A prime, X. Now, as you will notice, and as you learn later, this expression is very important, especially for statistics. But let's see what we've got here. Look, here we've got prime. So this matrix is 2 by 1, right? So if here we have prime, it means we should have a row vector. So this one should be 1 by 2. And finally, this matrix in the middle is 2 by 2. So look, if I multiply those 3 matrices, I should get a scalar, right? Because all we will have left at the end has dimension 1 by 1. Well, now, all I wanted to do is to check whether the order in which I will be multiplying those matrices is actually relevant. I already told you that, that it should be, but let's check to be sure. Okay, so look, we've got here x1, 1, a, 1, 0, 0, a, 2, 2, and sorry, of course, x1, x2, and here we will have x, x1, x2. Okay, so look, what I'm going to take two ways over here. In the first way, I'm going to first multiply those two. Okay, what am I getting? Like this is 1 by 2, this is 2 by 2. I should end up with 1 by 2 matrix. So, a vector. Okay, so how does it go? X times x1, 1, and x2 times 0, so we get a1, 1, x1. And this is the first element. Then the second element, 0 out of this, x2 times a2, 2. a2, 2 times x2. And now we are multiplying it by x1, x2. So now we should get a scalar, as we learned, and we get that this is a11, x1 squared, plus a22, x2 squared. Okay, so this is the result we should get. Now let's see if the same happens if instead I'm going to multiply those two matrices first. So this, here we go, x1, x2, a. So this is 2 by 2, this is 2 by 1, we should get 2 by 1 result. And I've got out of this a11, x1, then 0, and then 0, a22, x2. Okay, now we've got matrices 1 by 2 and 2 by 1, so we should get a scalar. And then if I multiply x, I will get a11, x1 squared, plus a22, x2 squared. So we clearly see that this associative law works. Okay, now that we've covered operation laws, we can take care of some special cases of matrices. There are some special cases of matrices that are very important for the entire process of operations on matrices. And look, do we have such numbers in algebra? Of course we do. Like for example, and this is where we're going to start. In regular algebra, we've got a number like 1. If I multiply a number, any number, by 1, and the same will go, doesn't matter from which side, of course, I will get a. Now, the question is, do we have something similar in case of matrix algebra? And we do. And this special type of matrix is called identity matrix. And identity matrix is a matrix with ones on principal diagonal and is a square matrix with ones on principal diagonal and zeros everywhere Okay, first, we will be denoting identity matrix by I. Sometimes we will also denote here the dimension of the matrix by n. And remember, because it must be a square matrix, it means it can be either 1 by 1, 2 by 2, 3 by 3, 4 by 4. So all we need is actually one dimension, right? Now, so how will this matrix look like? Well, we can start with I1, and it will be just simply a scalar 1. Then, if we will have I2, it will be 1, 0, 0, 1. What you see over here is principal diagonal. Principal diagonal is the line going from northwest to southeast, and it divides matrix into two separate parts. Okay, now I3 will of course be 1, 0, 0, 0, 1, 0, 0, 0, 1. And I hope from this you can conclude how each next consecutive identity matrix will look like. Now, let's see if we can actually obtain the result that we had in mind at the beginning. So if I multiply matrix, any matrix by matrix I, will I get the same matrix? Okay, let's just say that our matrix A is equal to 1, 2, 3, 2 over 3. Right? So this matrix is dimension 2 by 3. Okay, and on this example, let's examine if this will actually work. But we need to notice two things. Okay, let's just say that first I want to calculate I times A. No, well, we are noticing that matrix A is 2 by 3. So for those two matrices to be conformable for multiplication, I need to be 2 by 2. Okay, so what we need to do now is just multiply. First thing we can notice is definitely, because this is 2 by 2, this is 2 by 3, the outcome will be 2 by 3, which is what we want. Okay, now let's see if we are actually getting what we want. So, 1 times 1 plus 0 times 2, 1. 1 times 2 plus 0 times 0, 2. 1 times 3 plus 0 times 3, 3. 0 times 1 plus 1 times 2, 2. 0 times 2 times 1 times 0, 0. 1 times 0 times 3, 1 times plus 1 times 3 is 3. Well, definitely it worked from this side. But what if I want to now multiply A, which is 2 by 3, by I, again, look now, for them to be conformable for multiplication, this needs to be of dimension 3 by 3. Okay. So now let's see whether we get the same thing. Okay, and now we can notice that because this is 2 by 3, this is 3 by 3, they are conformable for multiplication, and the outcome should be 2 by 3, which is the one we wanted. Okay, so now, oh Jesus Christ, I'm sorry. Okay, we got 1, 0, 0, 0, 1, 0, 0, 0, 1. Of course, this needs to be 3 by 3. So, we start multiplication. Okay, 1 times 1 times 1 plus 2 times 0 plus 3 times 0 gives us 1. Now, 1 times 0, 2 plus 0, 2. 0, 0, 3. we've got 0, I'm sorry, 0, 0, 0, and finally we have 2, 0, 3. And exactly, this is the result that we've expected. And now we can say that identity matrix works as 1 in case in matrix algebra, works as 1 in just as 1 in regular algebra, and we get that A times I is equal to I times A, and this is equal to A. Okay, so what should we do next? Okay, now identity matrix is a very specific, is an example of one more matrix that we should discuss. This is idempotent, I'm sorry. Matrix. Idempotent matrix is a matrix that remains unchanged regardless how many times we multiply it by itself. Okay, so generally we would have a matrix that A times A times A times A is equal to A. And please, let's just say try this at home with I3 and make sure that this is result you are actually getting. Okay, the next special number in regular algebra is 0. How does 0 work? Well, it has two very important properties. First, if I have some number A and I add 0, it's the same as if I and I get that this is A. Then there is a second property of 0, that 0 times A is equal to A times 0, and it's equal to 0. Now we need to make sure. Now we can ask whether we have the same type of matrix in matrix algebra. And we have, and it's called either null matrix or 0 matrix. Alright? We will be denoting it by 0. Okay. Null matrix is a matrix with zeros as its elements. Okay, look, basically speaking, this property will work. Look, so this is a matrix where all the elements are equal to 0, right? So, look, we will have that A plus 0, assuming that A is m by n and 0 is m by n, is the same as 0 plus A, of course, still m by n, and this is equal to A, m by n. Look, you can very easily prove it. Okay, let's just do this one as well. So, we've got this. some collections of zeros, right? They are of the same dimension. So we get out of it that this is Aij. Alright. It doesn't matter from which side we are going to start. Okay, but of course there's something that I would like you to check at home, but we also have that if we have A m by n, we have A m by n times 0 m by n by p, we will get null matrix m by p. And of course 0 times A, if we have this matrix, let's just say n by p, this matrix p by q, we will get 0 matrix n by q. Okay, so now we actually show that there is a little bit more similarities between what we can see in regular algebra and what we see in matrix algebra. Okay, so but before we settle on this, let me talk about idiosyncrasies of matrix algebra. So look, there are some cases where we expect some result and we could extrapolate it from regular algebra to matrix algebra, but actually even though it seemed intuitively plausible, we should not do it. This is what we call idiosyncrasies. Idiosyncrasies are some specific features not present anywhere else. Okay, and let's consider a case like that. Okay, in regular algebra, we've got that if we have a number a times b and it's equal to 0, this means that either a or b must be equal to 0, or both, right? But if we know, for example, for sure that a is different than 0, if we multiply by some number we get 0, b must be 0. In matrix algebra, we can get the same outcome, we can get this outcome without resulting to null matrix. And let me show you how this works. Okay. So if I have matrix 2, 4, 1, 2, and matrix -2, 4, 1, -2, let me multiply them and see what happens. Okay, so we've got 2 times -2, -4, 4 times 1, 4, 0. 8, -8, 0. -2, 2, 0. 4, -4, 0. So look, actually, in case of matrix algebra, it is possible to multiply two matrices, out of which none of is a null matrix, and still obtain null matrix as a result. Okay. So now the second thing we should discuss is uniqueness, and again we will see an example that if a times b, let's just say if I have two numbers in regular algebra, a and b, let's just say a is different than b and it's different than c. So those two numbers are different, right? Now, so if a times b, if we have a situation a times b cannot be possibly equal to a times c if those numbers are the same and those are two different numbers. So we have this uniqueness property that if A times B is equal to some number, then if A times C is also equal to some number, then B and C must be the same. But look, in our, as it turns out, again, in matrix algebra, this doesn't need to be the case. So let me use one more example. Okay, so we've got two matrices. C. Okay, let's matrix C be 2, 3, 6, 9, and matrix D be 1, 1, 1, 2. And then we will have again matrix C 2, 3, 6, 9, and matrix E, and matrix E is negative 2, 1, 3, 2. Okay, look what happens as I multiply those matrices. Okay, so over here, 2 plus 6, 8. 6 plus 9, 15. 2 plus 2 plus I'm sorry, of course, here we have 5. 2 plus 3, 5, right? Then we've got 2 plus, which is 8, and 6 plus 18 is 20, is 24. Okay, now let's see what we get over here. We've got negative 2, negative 4, plus 9 is 5. We've got negative 12, plus 27, that's 15. So we've got 2 times plus 6, which is 8. And finally, 6 plus 18, 24. So, what do we see in this case? That this property of regular algebra doesn't work in matrix algebra, and we can actually obtain the result, the same result out of even though we are multiplying the same matrix by two different matrices. And I assume that this video has been going for quite a long time, so let's just say we're gonna stop at this moment, and in the next video we're going to discuss transposes and inverses. Okay, thank you for your attention and see you in the next video.